me parece, para el tipo de problema que vos estás haciendo es agarrar las fórmulas de suma. Ya te cuento cómo termina. Me parece que lo que hay que hacer es encontrar una relación. All right, so I wasn't sure, I'm not really sure where I left off last time. But remember, what I'm aiming to prove is that higher cohomology of quasi-coherent sheaves on affine schemes vanish, which is Serre's theorem. And what I started proving, and I think we finished this one, but just in case, is that, so we started proving that the higher cohomology of Flaby sheaves vanish. And to do so, we looked at a sequence like this. Of sheaves on a topological space X, and F was Flaby. Yeah, so I think I proved the first part, but not the second part. But anyway, so let's prove the first part again. So if F is Flaby, I want to prove that the first homology vanishes. So I want to prove that the global sections is exact. Is exact. So I think this we did prove last time. But just in case, since we were rushing, let's prove this. So let's grab a section here. And we can't really pull it back to G. We can only pull it back locally. I think this was more or less what we did. Anyways, so what we know is that you can pick up for each open U, well, you can pick up a U which is small enough, or you can take covers of X by small enough U's such that you can restrict your S to U. And then there exists a lifting of that S to U here. So let me call it in a different way. So we can restrict this to some T that depends on U. This is a section on G, but not on all of X, but on all of U, such that the image, if I call this map pi, such that pi of T U is SU, which is S restricted to U. And we can cover X by this opens, by this little opens U. So what we did is we grabbed the collection of opens like this, US and UTs. I think I was calling what I'm calling now S, I was calling them, when I'm calling T, I was calling S last class. But we pick collection of opens U and T, which this is U, an open in X, T, a section in G of U, satisfying that condition, such that T is the restriction of S to U. Or rather, pi of T is the restriction of S to U. And this is an order set where we declare that this is less or equal than U prime T prime if U is included in U prime and the restriction of T prime to U, or the other way around, the restriction of T, no, that's right, T prime to U is is t. Yeah, so u is included in u prime. And we use Zorn's lemma. By Zorn's lemma, I think we did this last time. There exists a maximum. U and t with those properties. This is clear because if you have any chain like this by inclusion, just take the union of all these u's and take the corresponding limit of t. They are all included inside of x. So since there's a maximal ut, then just I claim that u has to be equal to x. Let's suppose for the contrary, so let's suppose in the contrary that u is not all of x, u is not all of x, and pick a point in the complement and pick an open neighborhood of that point. You can make it small enough. And again, since I can lift small sections of H to G, I can actually pick up that S restricted to V now. So we can pick up a TV such that pi of TV is equal to SV, which is S restricted to V, and here TV is a section of G of V. And now, if you make this V small enough, what you have is you have a TU, we have a TV that I can restrict to the intersection, U intersected V, this to U intersected V, and both of them map by pi to S restricted to U intersected V. So both of these guys map to the same object. So if I take their difference, which is a well-defined section in this intersection, pi of this is 0. So that means that there exists some STR, some R in U intersected V, that maps to these guys. So this is a section, I shouldn't say R in restricted. There's an R, which is a section of F in U intersected V. That maps to do I want to map it to this difference, or do I want to map to one of them? I think this is fine. So I'm going to take this that maps to this TU minus TV, such that if I call this guy iota, this was my map of shifts pi, such that iota of R is equal, well, this is only defined on U intersected V. I'm going to change this in a second, but this is TU minus TV. But now F is flabby. So I can take R to be defined on all of F of V. So I can change the name, just call it R bar if you wish, but I'm going to call it R, that it's a global section of F of X, whose restriction to U intersected V is this R. So I'm abusing notation. So R restricted to U intersection V is this R here. So the point is that this R is well defined on all of X, and it restricts to this difference TU minus TV on the intersection of U and V. So what I can do is, so I'm very bad at this, so TV plus R. So I can look at TV, and I can add R, or iota of R. Now this guy is well defined everywhere, and this guy is only defined on V. Okay? And pi of this thing Since this guy is defined everywhere, but it's in the image of iota, pi of that is 0. So pi of this thing is S, but it's only defined on V. And pi of this guy is also S, but this is only defined on U. But on the intersection, pi of TV plus iota of R, if I restrict these guys to U intersected V, this is the same as pi of TU when I restrict to U intersected V. Because this is S restricted to U intersected V. So I have two sections, one on V, which is this guy. It's defined on all of V. I have another guy that is defined on all of U, is this guy. And they agree on the intersection. So since I have a sheaf, this is a sheaf H of G. They are sections of G on U and on V, and they agree on the intersection. Therefore, there exists a section T union U union V, which is a section of G on U union V that agrees with this on that agrees with this section on all of V and with this section on all of U. And it's defined on an open set that is larger than U by definition. And this guy, pi of this section TU union V, is equal to S restricted to U union V. And this is absurd because U was maximal with that property. And X is strictly not in U. So this is a strictly open, a strictly larger open set containing U. So that's absurd. So U was maximal. U was all of X. Therefore, for each S, this collection here has U equal to X. Therefore, there is a lifting of the full section S to T. So this sequence is exact. Oh, no, this wasn't the full lemma. Yeah, so the way I've written it, it is. So the second part of this lemma is that in the same situation, if F, G, H is an exact sequence of sheaves on X, and F and G are flabby, then H is flabby. Okay. So let's grab an open set and a sub-open set. So what I would want to say is that I need to prove that the restriction from H of U to H of V is surjective. And what I know is that F and G are flabby. So what I know is that G of U to G of V is surjective, and that F of U to F of V is surjective. But I claim that the surjection, claim we have a surjection from G of U to H of V. I claim that this is surjective. And the reason why this is surjective is because if you have a sheaf that is flabby, so if F is flabby, then obviously the restriction of F to an open as a sheaf on the open is flabby. So if you have an exact sequence of sheaves and you restrict them to opens, just call whatever you want the quotient. Restricting to an open might not be might not be exact. But the thing is that the restriction of this guy is Flavi, and I can use this lemma, where I need the, so I'm going to restrict this to U. I'm going to look at the corresponding sheaves, and I'm going to look at the restriction of F to that open U. This guy is Flavi, therefore on global section this thing is exact, which is what we just proved. We only needed the first guy to be Flavi. So from that you're going to get that the map from G of U to H of V is surjective. But this map here factors through this surjection, well, this map from H of U to H of V. So this map here factors through G of V, which is surjective, to H of V. Well, this is surjective because G is Flavi. And this guy here, map, is surjective. And it factors through the H of U, H of V. Because it comes from G of U. So this surjection here factors through this map like this. And this is surjective because of the exactness of F of U to G of U to H of U that we proved before because F is Flavi. So this guy is surjective, and this guy is surjective because this guy has to be surjective. Okay, so we have two things. We've proven that if I started with an exact sequence of sheaves on X, and F is Flavi, therefore on global sections this sequence is exact. And if this and this are Flavi, then this guy is Flavi. So now let's look at the long exact sequence in homology, in cohomology, that I get for these sheaves. Well, remember, homology, I really mean just the derived functor of global sections on X. So this is, you get an exact sequence of abelian groups, and you just take the derived functor of that functor. So the first step is that you get this. So now let F be a sheaf, be a Flavi sheaf. And take a resolution. You don't even need a resolution. Just take an injection into an injective object. So this is an injective sheaf. And I did prove that the category of sheaves of abelian groups has enough injectives. So this always exists, and let H be the quotient. Now, F is Flavi. Why? I is Flavi because we proved that injective sheaves are Flavi, and therefore H is Flavi. So this is Flavi. Last class we proved that every injective sheaf is Flavi, and therefore H is Flavi by that lemma. Let's look at long exact sequence in homology, and we get R0, which is global sections. R0 is global section of this, R0 of global sections this, and the first guy is going to be H1 of F. So this is our R1. And then we get an H1 of I. Now, injectives were adapted, so the first derived homology of anything of an injective is 0. And this sequence is exact because of the lemma. Therefore, this map here is surjective. And if this sequence is exact here, the image of this map has to be equal to the kernel of this map. And the co-kernel of this map is 0. And this guy is 0. Therefore, this guy is 0. So by exactness of the long exact sequence, H1 is 0. And now we just look at the other terms in that sequence. So from there we got that H1 x f is 0. Okay, so in general, what will we get? Well, I'm going to look at the long exact sequence, and I'm going to find that I'm going to have the ith homology of H mapping to the I plus 1 homology of F, cohomology of X with coefficients in F, mapping into the I plus 1 cohomology of X with coefficients in I, and coming from the ith cohomology of X with coefficients in I. But this is 0 because I is injective, and this is 0 because I is injective. Therefore, this is an isomorphism. Now, H and F are Flavi, and I can use induction. Since H and F are Flavi, and I already proved that H1 of any Flavi sheaf is 0, I can do induction in I. So if I know that the HI homology of any Flavi sheaf is 0 for I less or equal than the I that I want to check, then I know it for I plus 1. Okay. All right, so this implies that HI of X F is equal to 0 for every I bigger than 0, which is what I wanted to prove. All right. Okay, so this is more or less the point that we should have stopped last time. I'm not going to do much more today. I'm just going to prove that Serre's lemma. But the thing is that now we know that Flavi sheaves are adapted for that functor of taking global sections. And these are sheaves of abelian groups on any topological space, so it didn't require any alt-right machinery. Okay. So as a corollary of this, if you have a sheaf on a topological space X, and you pick a quasi-isomorphism with a complex of Flavi sheaves, then we know that the ith homology of X with coefficients in F, this is going to be equal to taking global sections of the complex G. Now this is a complex, and take the HI homology of this complex, cohomology of this complex. And the reason for that is just the fact that Flavi sheaves are, the proof is we just checked that Flavi sheaves are adapted to gamma. We have this general lemma that if we have a category that is adapted to our functors, namely that our functor takes acyclics to take objects, acyclic complex on this category to acyclic objects, and this is exactly what we just checked, then in order to compute our derived functor, we can just replace our object by a complex in that subcategory. In this case, the subcategory is the full triangulated subcategory of complexes whose objects are acyclic, are Flavi sheaves. Okay, so I can compute cohomology of sheaves by looking at Flavi resolutions. And this is nice because we're going to use this in the following situation, that if we pick an injective sheaf on X, what we're going to do is we're going to look at the restriction of this I to an open for u an open in X. And this is flabby. I is flabby, therefore that restriction is flabby. So if you have a sheaf F and its injective resolution that you can use on X to compute cohomology, what you can do is restrict this guy to U and restrict your injective resolution to U, and now this is a flabby resolution. And you can use those to compute cohomology. So in particular, we get the following situation. Let's look at a map of topological spaces. And let's grab F a sheaf on X. The question is, we have this derived functor. We've seen that the push forward was left exact. I've defined last time a push forward between sheaves on X and sheaves on Y. Remember how was this thing is that you've gotten here the push forward of F, and you wanted to evaluate this thing in an open V, an open of Y. This was defined to be F of F inverse of V. This thing is open on X, and you take sections of F in there. So this is a well-defined functor here, which is left exact. Therefore, we have the derived functor of this push forward. And the question is, what is this? Well, by definition, this thing is, or by construction, this thing is the same thing as applying our functor to our injective resolution. As an object in the derived category, this is the same. So that was the way that we computed derived functors from the derived category of sheaves on X, the bounded derived category of sheaves on X, or bounded below, to the bounded derived category of sheaves on Y. And this works. But okay, so from here, we get that the ith derived functor on F, this is the ith homology of this sheaf. But, well, that's a sheaf. This has to be a sheaf on Y. What is that sheaf? I have some space here. So let's look at what is this sheaf here. So this is a sheaf in an open set Y, in an open set V. This sheaf is, well, by definition, this is a complex of sheaves, which are this push forward of these guys, and I'm taking the ith cohomology of that complex. Okay? So what I need to do is evaluate these sheaves in this open and take the cohomology. And this, I know how to evaluate them because it's, therefore, the cohomology of this push forward of i's. This is a complex of sheaves that I can evaluate at V. Now that I get a complex of abelian groups, and I take the homology of this. But this is the same thing as HI, as, well, the push forward evaluated at V. By definition, this is the same thing as looking at this I at F inverse of V. And take the homology of that. But now I can continue there. So I have my i's at F inverse of V, and I'm looking at the ith homology of this. But what are these? This, by definition, is also the set of global sections. So these are global sections on F inverse of V of the sheaf, which is I restricted to F inverse of V. So this is a complex, and I'm taking the ith homology. But on the other hand, this is a Flaby sheaf. This complex of sheaves, when I restrict it to F inverse of V, is a Flaby sheaf. It's a Flaby complex. It's Flaby. And by the comment that I said there in the corollary, this is a Flaby resolution of F. Restricted to that thing, same thing. So if I'm going to be looking at the ith homology of global sections into that thing, this by definition is the same thing as the ith homology of my sheaf now on F inverse of V, which is an open of that sheaf F restricted to F inverse of V. And this is the ith sheaf homology of this sheaf on this open. And where I started from is the right functor of the push forward. Of this guy, of F, evaluated at V. So the corollary is that this sheaf, this guy, is the sheaf on Y associated to V. You give me the ith homology of the F inverse of V of your sheaf F restricted to F inverse of V. And this is again for any sheaf of abelian groups on any topological space X. Okay, so we know how to compute derived push forwards because we know how to deal with Flaby sheaves, because we can take Flaby resolutions. Okay, and I want to exploit this. So before I prove Serre's lemma, let me give you a definition. So for now on, I'll take X to be a topological space. And I'll take B to be a basis of the topology of X. This is going to be fixed. We're not going to have many choices in the cases that we're interested in, but for now, this is general. So I have a topological space and its basis. And I'll say that, definition, a sheaf F satisfies property Pi if for any section in Hi in the ith homology of F, there exists a covering. Oh, I is a bad idea. U alpha is a covering of X by elements in B. of x by elements of V, of the basis, such that the image of A in HI of U alpha of F restricted to U alpha is 0. So I need to explain what this means. So I need to explain what do I mean by the image of A there to that cohomology. So first of all, cohomology was functorial. This was defined as the cohomology of the derived functor associated to global sections. And in particular, for any U, remember that we have push forward and pull backs were adjoint. So we have a natural map from, I would say J, I'll say like this. I push forward, I pull back of F, where I is the inclusion from U into X. So this is just the restriction. I never define pullback. I've defined pre-images of shapes. So this is just the restriction of F to U, and this is just the push forward by 0. Both of these things I defined. Actually, the push forward is defined in that board now. So this is the natural map. And since we have this natural map, you get a map in cohomology. So for any section in HI with coefficients in F, you get a section with HI with coefficients in this sheet on X. On the other hand, it's clear that you have a map from HI of X with coefficients in the push forward. Probably I is a bad idea. Iota push forward of a shift G to HK of U with coefficients in G. This is for any shift G in U. So that's what I mean by this image of A in HI of X to a cohomology class in U of the restriction of F to U. So for each alpha, we have this thing. We have a natural map from this cohomology to this cohomology, and I'm going to require that the image of any guy here is 0 here. Notice that this does not mean that HI is 0 for F. Of course, if the ith cohomology of F vanishes, F satisfies property I. Now, the important statement about topological spaces is that any sheaf satisfies property 1. No, that's false. That's clearly false. But if X is compact, this is true. If X is compact, this is true, and moreover, this covering can be taken to be finite. So any sheaf on a compact space satisfies this property, even though it's not necessarily true that H1 of any sheaf is 0. Clearly, there are sheaves whose H1 is non-zero, but still, their images on H1 for any basis of the topology is 0. So let's prove this statement, which is not entirely trivial. Okay, so so I want to grab a sheaf, I want to grab a class in H1, and I want to prove that I have this, the images on elements in a basis. I can prove that their images in H1 are 0. So let's prove that. Okay, so let's grab our sheaf, F, and let's put it inside of an injective sheaf. And let's consider the quotient of that sheaf. So this is a sequence. So this is an injective sheaf. I know that my sheaf is inside of an injective one. Q is the quotient So this is an exact sequence of sheaves on X. Notice that, so I'm going to see in the next term in the cohomology sequence, I'm going to see the object that I'm interested in. So I have a sequence fx, ix, qx, h1, xf. This is where I'm interested in. This is where my A lives. And the next term is an h1 of I, which is 0, because I is injected. So here's my A, and I want to understand the image of this guy for each u alpha into u alpha f, where u alpha is just any element in this basis. So I want to understand that image of this guy. Now, since cohomology is functorial, I might as well just take a preimage of A that I know it exists because the sequence is exact. So I know that I can lift this guy here to some A bar here, and I can map it to the restriction of this Q to u alpha. Because this map is very simple to understand. If I have a global section of Q, I just restrict it to u alpha. And then I can look at what is the image of that guy here. Okay? All right, so well, but so what's the thing? I could try to restrict these three sheaves to u alpha and see what I get. Now, of course, I have this f restricted to u. I have my I restricted to u. And I have the quotient. Let me call the quotient q bar u alpha. So this by definition is the quotient of these two. On the other hand, I have this guy which is q restricted to u alpha. And I want to compare these two. Okay? So so I claim that there's an injection from this sheaf to this sheaf. Okay? This sheaf is by definition the quotient of these two restrictions. Restricting is not right exact. So it's not necessarily true that I still have this surjection. Right? So it's not necessarily true that I have a map from u alpha to this guy that is still surjective. I still have this map, and I still have exactness here, but I no longer have exactness here, because this restriction to u alpha is not necessarily right exact. Okay, but it's still true that I have this map here with any section of of y to u alpha. I can just restrict it to I can map it to q by the same map that I have here. If I call this map pi, and I call this map iota, sections of these guys are sections of the full I in the intersection of my v with u alpha. So those are sections of these guys on v, which I can just map by being a section of I to q. So this map is well defined, and since this guy is exact, the image of this guy is 0 here. So that means that this map factors through the quotient of I modulo f, which is exactly this quotient here. So this map here factors through this quotient, and this guy is now an injective map. Okay, so any section of q of this sheaf here, which is a section of I modulo a section of f, I can view it as a section of Q restricted to U alpha. All right. So I have my A, which is a section of an element of H1 of XF. Since this sequence is exact, then I can lift that A to a section of Q of X. This is a global section of Q of X. Now, this sequence is an exact sequence of sheaves. I cannot lift this A bar to a section of I, but I can locally lift it. Okay? So what I know is that I can choose, there exists a covering Now I'm going to use for the first time this U alphas, which is my covering of X. And since X is compact, there's a finite covering. Such and sections, let's say S alpha. These are sections of I in U alpha, such that, what's the name of the map? Pi of S alpha is equal to A bar restricted to U alpha. Okay. So this is the fact that the map I surjects into Q. It's a map of sheaves. Now the thing is that I is flabby, because I is injective. Now I is flabby. Because I is injective. This means that those sections that I just constructed of I in U alpha can be global. I can choose them to be global. What did I call them? S alpha? I'm going to still call them S alpha. Such that pi of S alpha, when I restrict these guys to U alpha, they are equal to A bar restricted to U alpha. So I have my sections here now, S alpha, for each U alpha. But they are all global sections of this guy. And what I know is that if I map this guy to here, well, they might be different than these two sections. They are global sections. I mean, this map is well defined on global sections. So I get some sections here. They might be different than this A bar, but the restriction to U alpha is equal. So that means that when I pass to this quotient, I look at F restricted to I restricted to U alpha. This guy goes to the same image as this A bar here. Okay. And now, of course, the image of this A in H1 was the image of this element. But this element is coming from a global section of I. So this has to be 0 here. Because the long exact sequence in cohomology for this sequence of sheaves, now for this sequence of sheaves here, will have sections of F, sections of I, sections of Q bar, H1 of F restricted to U alpha. And the image on this H1 of the map from Q, the quotient, to this H1 of F of U alpha to F restricted to U alpha is going to be 0 because this A bar is in the image of something that comes from I. Okay. So this proves that any sheaf on a compact topological space satisfies P1 with respect to any basis. Okay, the second piece is the following lemma. Suppose that you have a sheaf that has a stronger condition. I'm going to require now that the cohomologies of these spaces are 0. So here I didn't require that these cohomologies are 0. I only required that the images of this A in H1 were 0. Now I'm going to require that these cohomology are actually 0. So suppose that for every k less than I and bigger than 0, the cohomology of your sheaf F, well, restricted to U alpha, of U alpha, of your sheaf F restricted to U alpha is 0. Then F satisfies property I. Remember, property I says that if you have a class in HI of your sheaf, then it maps to HI of your U alpha, F restricted to U alpha, to 0. Oh, I think I added at some point this equal to 0 just to exemplify, but this meant the image of A in this is 0. If this was 0, then it's obvious that it satisfies property I. Okay, so now I'm requiring that these HIs are 0, well, HKs are 0, but for less than I. And I'm going to prove that if I grab an element A in HI of the full space X with coefficients in F, then it maps to 0 in HI of each one of these U alphas. Okay, and then we just use the same sequence that we did now. So I'm going to use the same sequence here. So you inject your F into an injective. I have this sheaf on a topological space. Both of them satisfy property P1 because I proved that any sheaf has satisfied property P1. So what I'm going to do is I'm going to do induction in property I for, I'm going to do induction on this statement for those both sheaves F and Q at the same time. Okay. So if you look at the long exact sequence in cohomology, well, let's do the first one first. So the first one says that we're going to have f of x, I of x, that sequence that I just wrote there, Q of x, H1 of x f. This is not necessarily 0. Oh, now it is 0. Not necessarily 0. This is because H1, the next one is I, which is H1 of I of xi. And then the next ones are going to have H, 0. Hi of xf xq into hi plus 1 of x f 0, this being an isomorphism. So now do the same thing for this restriction. But now I want to do something different. So I want to notice something. So before I took the quotient of f restricted to u alpha, I restricted to u alpha, and I call this q bar. And this injected in this q restricted to u alpha. So what is the co-kernel of q modulo this q bar? Okay. Now notice that in this case, where H1 of u alpha of f restricted to u alpha is 0. This is a requirement of my sheaf. So I started with my f, that satisfies, I already know that it satisfies property 1. So I want to check what happens if for this I bigger than 1. Okay, so here I is bigger than 1. Otherwise, this condition is completely empty. So now I know that k equal to 1, this space is 0. This is something that I wasn't requiring before. Before I was just only looking at classes in H1 of X and mapping to a class in H1 of U alpha and checking that the image was 0. But now this group is actually 0. H1 of F restricted to U alpha is 0. So that means that these two guys are equal, are isomorphic. This is because H1 of this guy is 0. So since H1 is 0, that means that when I look at global sections, I'm going to get this, I'm going to get global sections of this, I'm going to get global sections of this, and I'm going to get this group that is 0, because that's the next step that appears here. So this is now 0, and this sequence is exact on global sections, which is the same sequence here by definition being exact. So now that means that when I look at the sequence of sheaves f, I, and its quotient, I can restrict that to U alpha, and I'm going to have this sequence f restricted to U alpha, I restricted to U alpha, and Q restricted to U alpha, and this is exact. So now the long exact sequence in cohomology for this guy is going to give me that Hi of U alpha of Q restricted to U alpha is isomorphic to Hi plus 1 of U alpha of F restricted to U alpha. And of course, I have this map here, and this map here, and this diagram commutes. Okay, so now what I wanted to prove is that this sheaf F satisfies property I. And I want to do this by induction. So, so we see that it's enough to prove that if F satisfies property I plus 1, it's the same thing as Q satisfying property I. In particular, this map here is 0 whenever I is equal to 1. This map is 0. This is 0. Because we've proven that this is 0 for any sheaf, that the map from H1 to these H1s are 0. So that means that this guy is 0, and F satisfies this property P2. Of course, we've used already the condition, so notice that this is hiding that we've already used that H1 of U alpha with F coefficients of U alpha is 0. So this guy implies that F satisfies property 2 because of this condition. And now in general, if Q satisfies property I, then these maps are 0, then F satisfies property I plus 1. Okay? Since F satisfies property 1, we prove that Q satisfies property 1, we prove that F satisfies property 2, then it proves that Q satisfies property 2, which means that F satisfies property 3, and so forth. All right. So, okay, so let's finish with the theorem of Serre. So Serre's theorem, Serre's vanishing theorem. And this is the first time that actually requires some knowledge of at least some definition. So I'll just give a definition, I'll make a statement, but probably I won't prove it. If I don't find anything to give lecture on Wednesday, I'll prove this statement that I'll use today. So let X be an affine scheme. And F be a quasi-coherent sheaf on X. then hi of xf is 0 for every I bigger than 0. So a few definitions are in order, at least to have everything defined. And I'm going to be leaving one statement that I won't prove today. So first of all, what is a locally ring space? It's a topological space X space together with a sheaf of rings in X, and such that for any point in X, for any point in X, then the stock of this sheaf, or the localization of this sheaf near that point X, is a local ring. They form a category, and so I'm not going to repeat everything here, but they form a category as follows. If you give me a map, so I need to define what is a morphism of locally ring spaces from XOX to a locally ring space YOY. And this is a map, a continuous map of topological spaces from X to Y. And the following, we have this, it's going to be the same. We have this sheaf of ring on Y, which we can pull back by F to a sheaf of rings on X. And I want a morphism that I will call F sharp to OX. And this should be a morphism of sheaf of rings. So not only is a morphism of sheaves, well, let me just write what that means, of sheaves of local rings. So this is in particular is a morphism of sheaves. So it needs to send for open sets here sections to sections. And for each open set V, then it's going to send, if you give me on V two sections, A and B, then F sharp of A times B is equal to F sharp of A times F sharp of B. So that's the fact that it's a morphism of sheaf of rings. So this is for any A, B sections on A and any V. V is an open in X, any open. And finally, what I would want is that for any point, for any point in X, I have this OX, which is a maximal, which is a local ring, and I have this F inverse of OY at X, which is a local ring, and I would want that this F sharp sends the maximal ideal of this guy into the maximal ideal of this guy. So I have these two local rings, so I would want that the preimage of the maximal ideal of one is in the maximal ideal of the other one. So those are they form a category with this condition. And examples of those are holomorphic manifolds, complex manifolds, and the sheaf of holomorphic functions. Those are X is a holomorphic manifold or a complex manifold, manifold, and OX is the sheaf of holomorphic functions. on X. This works. X is a smooth manifold, a smooth real manifold, and OX is the sheaf of C infinity functions on X. Works. X is a topological space, and OX is just the sheaf of continuous function on X. Works. Okay, so in this level, this is quite general. Now, the case that we are interested in that says there is X is an affine scheme. So X is an affine scheme means something that I will not describe, but as a set, let's say that R is a ring. R is a ring. Then this is, as a set, the collection of prime ideals in R. And this set has a natural topology called the Zariski topology. Which makes this into a topological space. Becomes a topological space. Now I claim that there is a natural sheaf of rings in that space that I will not even aim to construct, but I want to use some properties of that sheaf. And perhaps I'll do it next time. So I claim that in this space, in this topological space, there exists a sheaf of rings, OX, a sheaf of rings, a sheaf of local rings. That satisfies the property that you want, namely, on a point in X, by definition, is a prime ideal. This, by definition, is a prime ideal on R. And this guy needs to have, at that point, it needs to have a local ring. And there's a natural local ring that we have, which is the localization at the prime ideal P. So I'm telling you what the stalks of this sheaf are at each point. What the local rings of the sheaves are at these points are just the localizations of the corresponding prime ideals, which are the points in X. But I need to construct it as a sheaf, which I want for a second. But a property of arbitrary locally ring spaces is the following. If you give me a sheaf, let me give you a definition. A sheaf of modules, a sheaf of OX modules on a locally ring space is a sheaf of abelian groups. Is a sheaf of abelian groups that is naturally an OX module of abelian groups. Groups, let's say F, such that for any V, so you have this OX on V, which is a ring. We have F of V, which is an abelian group, and we will require that this is an OX of V module. So this makes this guy into an OX of V module. Compatible with localizations. It's similar to what I've asked here to have a sheaf of ring. When I say sheaf of ring, I needed these guys to be rings for each V and then compatible with localizations. Okay. So now once you have a sheaf of modules, global sections in particular, on X of F, by definition, this is a module. OX module. Right? So this is by definition. Just take V to be this total space X. Now, this guy here, I've told you what the stalks are. that for point P, this is the local ring, and I'm going to tell you now what the global sections are. OXX is going to be the full ring R. So in particular for affine schemes, which are going to be sets, are going to be these guys, then what you got is a functor from the category of OX modules to the category of R modules that takes a sheaf F to these global sections. Here X is the spectrum of R. This is just all completely trivial. There's nothing to it, but it becomes interesting and non-trivial when I add some conditions. So what are examples of O modules? OX itself is an example of an O module. OX is an OX module because multiplication by itself satisfies the property of being an OX module. An OX module is called free, F, which is an OX module, is called free if it's isomorphic to OX to some power. So the functions into OX from any set I is an OX module, and that's a free OX module. And it's called presented if there exists a sequence of OX modules, two of them are free, and this is exact. So that's a presented module. And finally, it's called locally presented or quasi-coherent. If this happens locally. So what does this mean that this happens locally? Well, clearly a sheaf of OX modules, if I restrict this to a subspace, if you have a locally ring space, you take an open subset, it's still a locally ring space where the restriction of your sheaf of rings to that open. And if you have a sheaf of modules on the ambient space, you restrict it to the open subspace, it's still a sheaf of modules. So if I restrict a sheaf of modules to an open subspace, I still have a sheaf of modules. So the condition here is going to be as follows, is that I'm going to have a sheaf of OX modules such that there is a covering of X by some U alphas, and such that for each U alphas, I have O of U alpha. This is the same thing as O of X restricted to U alpha, to some set, O U alpha to some other set, F restricted to U alpha. And that exact. So that's a quasi-coherent sheaf. And I'm not going to say much more than that. I'm only going to say that this is an equivalence of categories when I restrict to quasi-coherent sheaves. And that's a non-trivial theorem that I want to prove. Perhaps I'll prove next time. So this is not an equivalence of categories in general. This is an equivalence of categories for quasi-coherent sheaves. Between R modules and quasi-coherent sheaves on O of X. Okay? So the trick here is to, given an R module, construct a quasi-coherent sheaf such that the global sections is your original module. And you cannot construct an arbitrary sheaf, you can only construct quasi-coherent sheaves. And this is the property that we will use of quasi-coherent sheaves in that proof of Serre's theorem. So yeah, I apologize. It's using something. It's using the fact that if you have a short exact sequence of quasi-coherent sheaves on the spectrum of a ring, then on global sections you get an exact sequence. It's not hard to prove, but it requires at least one lecture. All right, but I want to use the previous theorem that we proved. That was strong, and it was non-trivial to prove this lemma about O of X modules. So, okay. So let's start with our sheaf F, which is a quasi-coherent sheaf. It's a quasi-coherent sheaf on the spectrum on X, which is affine. It's easy to check that X is compact, that this X, the spectrum of a ring with the Zariski topology, is a compact space, compact topological space. And the basis is going to be of open affines. So this guy has a basis given by the spectrum of any quotient of R, of any localization of R. That's going to be my basis. I'm not going to use any property of this basis, so I don't need to specify it further. They're only going to use that it's covered by affine subspaces. Okay, I want to prove that the higher cohomologies of these guys are 0. And we're going to do the following. So I'm going to look at elements of that basis. So I can always cover my X as a finite union of elements in my topological basis. And I have a short exact sequence. Let me tell you first, let me write it first, what these guys are. So here F alpha is the restriction J alpha, push forward, J alpha, pull back of F. And J alpha is the inclusion of U alpha to X. These U alphas are the elements of the basis. So if you give me a global section of F, you just map it to the restriction to U alpha and just map to the product of the restrictions of your section in each one of the U alphas. And this is the quotient. By definition, it's the quotient sheaf. Now it's clear that this, oh, no, this is not clear. I haven't defined this. I've defined you what the pullback of a sheaf is. I haven't defined you what this pullback is, nor what this push forward is for O modules. So I told you what the sheaf pullback of a sheaf is as a sheaf of abelian groups, and what the sheaf push forward of a sheaf is as a sheaf of abelian groups, but not as O modules. However, let me take a shortcut here. And I'm using that these U alphas are affine. They are themselves the spectrum of some rings. Let me call these rings S alpha. For some rings S alpha, and we can make them very explicit. We can choose a non-zero divisor of R, a non-zero divisor. Let me call it F alpha. And then S alpha is equal to the localization of R at F alpha. So this means the ring of fractions of R divided by the inverses of F alphas. Now, there's an do I want to say this? Yeah, well, this U alpha is inside of X. And this corresponds to the map from R to S alpha that sends R to R divided by 1. So this localization is, yeah. Okay. So once I do this, then if you give me any R module, this was the same thing by this equivalence as giving you a quasi-coherent sheaf on X. So I started with my F. It's coming from an R module, which is the global sections of F. Then I can just look at the corresponding localizations to get modules over these U alphas. And these are modules over these rings. Therefore, they are quasi-coherent sheaves on these U alphas. And I'm just taking, which I can view them as R modules again, because R maps to S alpha. So I'm taking here this F alpha is the quasi-coherent sheaf on X, whose global sections are those modules F alphas. Okay, so that's, again, using this equivalence, these are quasi-coherent sheaves on X. Otherwise, if you know what the pullback and the push forward of quasi-coherent sheaf is, this is just the same thing. It's just restrict sections, and it's what we've been doing. A section of this sheaf is a section on any open U, and a section of this guy is a section of the intersection of that F to U intersected U alpha. So you can just, this map here is just the restriction of the section, nothing more. And this by definition is a quotient. The point is that this is quasi-coherent, and these are quasi-coherent, and therefore these are quasi-coherent. This is quasi-coherent, and that's not hard. The condition of being quasi-coherent is the fact that you have local presentations, and if you have local presentations for a sheaf, a second sheaf, then the third one has a local presentation. That's easy to check. So far the hard thing was this, and this is the only hard thing. So easy, Q is local, is quasi-coherent. That's easy. Hard, because it's easy modulo this, on global sections, this sequence is exact. I mean, of course, this comes from this exact, from this equivalence. The fact that this is an equivalence says that taking global sections is exact. But this is very strong, so we want to prove this, and I'll probably prove this in the next class, that if you have a surjection of quasi-coherent sheaves, then taking global sections is still surjective. On an affine space, of course. Okay. So finally, but I want to use this property. We know that any sheaf satisfies the property P1. Okay. So I would like to look at the global cohomology sequence associated to this sequence here. What is the global sequencing cohomology associated to this? Okay. So, well, this starts here, but actually the next term should have been H1 of F. Over alpha of X. Now, global sections of these guys are the same thing as the sections on U alpha, so it's fine. Now this is to Q of X. Here I should have put H1 of X F. And here I should put the the product over alpha of H1 of this guy's F alpha. So F alpha is the restriction of F to U alpha. So that sequence is exact. On the other hand, remember that we can take the map from H1 XF. We do not know that these guys are 0. But we know that this map is 0. This map is 0 because any sheaf satisfies property 1 because of property 1. So I don't care if this one is non-zero, but or if this one is non-zero, but this map is 0. On the other hand, this map is surjective because of this exactness for quasi-coherent sheaves. If I have a surjection of quasi-coherent sheaves, it's still like surjective when I take global sections. So that means that this guy has to be 0 because of exactness of this long sequence. The kernel of this map is all of this, and it has to be the image of this map, which is 0, because this guy is surjective. So that means that H1 of F is 0. For any quasi-coherent sheaf. And now just use the long exact sequence of cohomology. So now the long exact sequence in cohomology tells you that you're going to have HI X Q mapping. Well, let's start from before. We have some HI of X of U alpha, F alpha, the product of these guys to HI of X Q to HI plus 1 of X F to HI plus 1 of X of the product alpha of U alpha F alpha. And this is exact. Now, I'm going to do induction on I. These ones are affine. And these are quasi-coherent sheaves on the U alpha, which is affine. And I'm going to assume that up to HI, these guys are 0. I've already proved them for I is equal to 1. Okay? So these are 0. These I might not use that this 0. Okay? So I'm going to use this up to HI. So again, this guy is 0. But now this map is 0. And this is because of property the lemma. The lemma said that, well, in this case it's pi plus 1. The lemma said that if I know that hi on u alpha, hk on u alpha of these restrictions are 0 for every k less than I, in this case is I plus 1, then my sheaf satisfies property I. In this case is I plus 1. So my sheaf satisfies this property. That means that any class here maps to 0 here. So if I have any class here, it maps to 0 here. But this sequence is exact, and by induction, this sheaf is 0. That means that this guy has to be 0. Okay, so that's the proof of Serre's lemma, and we've used a lemma, which is the first time that I'm just on time. We've used this lemma that global sections is exact, so perhaps I'll prove this next time.